So today I wanted to talk about approximation of the smallest SLP, so the smallest grammar generating a string. But there is this small issue that I haven't finished the previous proof. Yes, well, on previously, whatever the day it was. So would you like me to try to reiterate this proof, or was it close enough to a proper proof that I do not need to do it? Okay, I will assume that it was close enough to the proof then. Okay, so in the smallest grammar problem, the thing that we want to do is we are giving some string, so we are or a word if you prefer, W, and we want to produce an SLP which generates this string, but we want the smallest one. Okay, the smallest, it might depend somehow on what exactly we mean by the size, but let's say we calculate the length of the right-hand sides. Okay, so here the right-hand side's lengths. Right-hand side's length. And it doesn't really matter what's the exact definition, because it turns out that even the decision variant of this problem, so given a word, decide whether it has an SLP generating it below some threshold, is NP hard. So we cannot, and it's NP hard in in many different variants. So what we can only seems what we can do is to, at least from a theoretical point of view, is to have approximation algorithms. Okay, so we will have algorithms that, given the word W, they will return some SLP generating it, and there will be some guarantee of the approximation ratio, which means that if G is the smallest grammar size, then what we can only guarantee is that we will return something of the size O of G times logarithm of the length of the word divided by G. This divided by G is some extra icing on the cake, but what's important is that our grammar is logarithmically, well, this logarithm is important, so they're logarithmically larger than the smallest grammar. Curiously enough, we only know a lower bound, so it's only constant one, so we only know that we cannot approximate it within a small constant fraction, and by small I mean something of around 1 + 1 / 8,000 something. Okay, so there's a huge gap between what we can do, which is a logarithmic approximation ratio, and what we know that we cannot do, which is some very small constant. And most of the algorithms that of the approximation algorithms that for the smallest grammar problem, they use somehow the LZ77, or at least theoretical variant of the LZ77, because it's under approximates the size of the SLP, which I will show in a moment. By the theoretical variant of the LZ77, we mean that we can represent a word as a concatenation of some smaller factors. So we have a word which is perhaps very long, and it is some concatenation of some smaller factors, such that one factor is either a letter or a factor appears somewhere earlier. So this factor can be seen that it's somewhere, or this factor can be found somewhere earlier in the string. So this factor does not need to exactly match some previous factor, but it's just somewhere as a word somewhere earlier. There are two variants of this LZ77, meaning whether this I will call this a factor, and this is its definition. Okay, so this is definition of a factor. And the thing is whether this definition and the factor can overlap. So in the simplest example, consider that we have just a very long sequence of A's. And if they can overlap, then of course this first letter needs to be different because it's the first letter, it doesn't appear anywhere else. But if we allow overlapping, then we can say that this factor just appears one letter earlier. Okay, and then this LZ77 factorization would be just of size 2. It will have just 2 factors. And if we do not allow such overlappings, then of course we would need to make those binary powers of 2. So the second one would also be 1 letter, the third one would be 2 letters, the next one would be 4, and so on. Okay, so there is of course a small difference, but nevertheless, of course, this one which allows overlapping is potentially smaller, so I will be using that one because it doesn't make any difference. The size of such factorization or the size of this LZ77 is just L, so the number of those factors. And what's important is that the greedy algorithm gives the smallest such factorization. And this is an easy thing that's usually proved in some data course or compression lecture. And this is because what one can prove inductively is that if we take the greedy factorization, then it's for each kth factor which it has, that this end of this k factor is maximal possible over all factorization of size k. So then if we have any other factorization of size k minus 1, of size k plus 1, then it will span somewhere here. Its previous factor will be, its last factor will begin somewhere here. So all of that, if we cut it off here as well, then this part also appears somewhere earlier. So we could also append it to our greedy factorization of size k plus 1. Okay, but that's relatively, I mean, this is a very simple proof. And this applies both to this overlapping and no overlapping scenario. Okay, so the notion of LZ77, is it clear? So this is a theoretical variant in the sense that usually if this is actually used in the compression, then there is some, you cannot go back arbitrarily large. So there's actually some sort of a window of last 1,000 or 2,000 characters, and your previous factor needs to be within this window of previous, let's say 2,000 elements. So this unbounded jumping is forbidden. Okay, any questions? No. Fine. So the thing is that if we have a smallest grammar, so if L is the size of the smallest of this LZ77 factorization, so the number of factors, and G is the size of the smallest SLP, then this LZ77 is smaller. Well, not larger than G. It's actually it's strictly smaller. And why it is so? So imagine that we take this G, well, the smallest SLP, and then there is some starting symbol, and there is the derivation tree. So we make just a partial derivation tree in the sense that each non-terminal is expanded once. Each non-terminal is expanded once, and this is the leftmost expansion. Leftmost expansion. So for instance, if here we have production to A again, then this one is not expanded, just this one. If this goes to B, C, and C goes to B, D, then this one is again not expanded. This can go to again D, D, then this one is not expanded. This one is also not expanded. And this D can go to A, B, let's say. Okay, and so the nodes that are expanded are this one, this one, this one, and this one. In order to show that this is actually okay, C is also expanded. This one is also expanded. In order to show that this is well defined, then one would have to show that actually if there is a leftmost expansion of, say, B, and the A is father of B, then A is also the leftmost expansion of A, but all of those follow relatively naturally. Okay, so if we calculate, and then this can be used to make this factorization, LZ77 style factorization, because if we have this A here, this corresponds in the word to some substring which is here, then this substring occurs somewhere earlier because this is not the leftmost occurrence of A. Okay, so this one has an earlier occurrence. Similar, this one has an earlier occurrence, this one has an earlier occurrence, and this B also has an earlier occurrence. Okay, so each one of those not expanded occurrence of the non-terminals can be used to can be just linked back somewhere to the left to some of those, to an occurrence to the leftmost occurrence of this A. So this gives an LZ77 factorization, well, LZ77 style factorization. That's not the minimal one, or at least not necessarily the minimal one. And then it remains to see that if we count how many nodes are expanded, then each rule is applied once. Each rule is applied once. So the number of non-terminals that we have here is just the sum of the rule sizes. So the, well, x goes to alpha is a rule. Okay, so we introduce as many non-terminals as the right-hand size of the rules, and actually we delete non-terminals in each of the production. So actually this size is, well, +1 for the S, but actually we also deduct some non-terminals, because each time when we apply the rule, then we remove one symbol from this tree as well. Okay, so this shows that given a grammar, we can make an LZ77 style factorization, which is of smaller size, or of that size as this grammar. So the smallest factorization of LZ77 is smaller than the smallest grammar, smaller or equal. Okay, and LZ77 can be effectively computed. So I gave some procedure, meaning that we can make it greedily. So let's say in the worst case, it can be done in quadratic time, but actually it can be done in linear time using some standard tools from stringology. Okay, so how to use this LZ77 for construction of the grammar? So there are several approaches, and perhaps the one that I would like to show is the most in style with what we said previously, but I also think that it's the simplest. Okay, so if we build a grammar, then we can imagine that we have a sequence of words, a sequence of letters, and each grammar is just a pairing. So some of the letters are paired like on the bottom level, then on the level higher we again have some pairing, then again some pairing, again some pairing of letters, and so on. So building a grammar is just building a pairing on top of the existing letters. Okay, and what we could do in order to build a pairing is just to make it naively. So first with the second, third with the fourth, and so on. So just build each letter with the, well, each letter at out position with the letter of the consecutive even position, and then iterate. So then we would make it like that. Oh, there's one left. Here like that, and somewhere of this form. But the problem is that this is somehow completely independent of how this LZ77 looks like. So what could happen is that this LZ77 tells us that there is a factor, let's say like this, which appears somewhere earlier, but it should look something like that. And the problem is that the factor which appears here and which appear here, then they are shifted by some odd number of positions, which means that the pairing of one of them and the pairing on the other of them are completely different. So that this previous, even though those are the same words, this previous pairing is completely different than the one that we are using. Okay, so it seems that this pairing is not the best idea. So we should use another one. Okay, just let me remove some of those. And which one we should use? So imagine that this pairing already has some letters paired. Then what we should do is to pair them exactly in the same way. If we want to make it somehow consistent, which should be good, then we should pair them exactly in the same way, well, in both of those copies. First, we cannot really, okay, like that. So this here we make those two paired, and for the last ones we make those two paired. And here there's a problem because we cannot pair this letter with that letter. Well, we can do that. So here the last element of this factor is paired with the next one. But here, if we make this pairing, then we do not know what will happen because the letter, well, most likely the letter to the right is different. So this is, let's say, A, and this is A, B, This is A, and this is most likely not B. So we cannot really pair it. So in order to say that they are paired in the same way, we just shorten the factor. So we remove this letter from this factor. We also remove it from the definition. Okay, so now the definition ends like here. And we make this letter into a new fresh letter. So into a factor of just length 1. Okay, and then everything looks more or less good. So we have our two factors which are paired exactly the same. And there is this extra letter, which is not such a big deal. I mean, it's just one letter per factor. Okay, so this is how we should, this is the idea how to build the pairing, so that we should iteratively pair the letters. And if there are some problems at the end of the factors, then we just split a couple of letters and hope that everything will turn out fine. Okay, that's not important. So what we are going to do is that we are going to devise a pairing, which will be nice in the sense that, first of all, it will be rather dense. So there will be no two consecutive letters that are both unpaired. So roughly we will shorten the string by 1/3 if we just replace every pair by a new letter. And maybe the last condition, that if we have a factor and and there is some definition of it, then the letters inside those two factors are paired in the same way. And this could be a little problematic if the definition has some pairing to the outside, or if the letter somewhere here is unpaired. So just to make it more concrete, we assume that if we have a factor, then both the last two letters are paired inside this factor, and the first two letters are also paired within the factor. Okay, this is a technical assumption. It could be dropped, and something slightly weaker could be done. And actually, to make it more efficient, it's better to have a weaker condition. But just for the sake of presentation, assume that both the first two letters and the last two letters of the factor are paired. This also ensures that nothing bad happens with a factor of length, that we forbid some very short factors. If we have a factor of length 1 and it has some definition, then we will just turn it into this free letter, because we cannot fulfill this second condition. Okay, so we'll just do it iteratively. Okay, so we take a word. Okay, some prefix of the word is already processed. And now when we process the following part, so imagine first what happens. So we are at some position I. So what we want to do is we want to pair this factor exactly in the same way as its definition. So there is a definition somewhere before, and we want to pair it. So since we want the first two elements of the factor, we want them to be paired, then if those two are not paired, then we will shorten the factor. Okay, so then we will make this letter a free letter, and we will continue with processing. Okay, so if the definition, the two letters of the definition are not, if the first letter of the definition is not paired, is not the first element of the pair. Okay, if it is a first element of the pair, then we just copy the whole pairing which is here, which not necessarily, it could pair also somewhere to the outside. Then we just copy it exactly the same way as it was in the definition, and we do something similar at the end. So it could be that at the end, so this is this part, it could be that at the end we try to pair this element with element to the right, which is usually a different pair than what it is at the definition. And we also wanted that the factor ends with two paired letters. So then we cut off the letters until we find something which is really, really paired. Okay. So this is this part. And as the last element, it could be that our letter at position I, from which we begin, is a free letter, which could be that it could have been from the very beginning, or we could have made it a free letter here when cutting out. And then we just look at the previous letter. If the previous letter is free and unpaired, then we pair those two letters. Okay, so if at this position, we would make it a free letter and move the factor here, and those two letters are unpaired, then we pair them as two free letters. Okay, and that's essentially the whole algorithm. There is one special case that we need to consider during some preprocessing. So before we process the word, we check with the previous algorithm, we check whether there might be a factor which has a definition just one element before. Okay, so its definition, the definition says that this element is that, well, this letter is the same as one before, but in such a case, this whole factor is just A to K. Well, because this is letter A, this is letter A, this one is the same as this, and so on. So all of those are just A's. So in this case, what we do is we shorten the factor by one element, which still makes it a power of A, and then we change the definition so that it doesn't start. So the definition of this factor is still of the form that it starts here. Okay, so this factor becomes one element shorter, but the definition still points at exactly the same place, which is well defined. And now what happens is that we change that the starting position is starting position of the factor is one position to the left. We change it that it is two positions to the left, and this is enough for the analysis of the algorithm. Okay, it could be that this factor was just one element and there's some special treatment. If it consisted just of one element, then we delete this factor and make it this letter a free letter. Okay, so first for the correctness of the algorithm, so we should satisfy those three conditions, P1, P2, P3. The first one says that there are no two unpaired letters. The second one said that there are some paired. First two elements of the factor are paired, and the last two elements of the factor are paired. And the third one says that the pairing is the same for the factor and for its definition. So this one is is just done by the actual construction. So what we did is that we, as soon as we found something, the beginning of the first element of the definition is paired appropriately, then we just copied the pairing, and then we fixed something at the end by removing some letters from the end. But nevertheless, for the whole factor, we just copied the pairing from the definition. Okay, so that one is satisfied. For this first one, so there are no two unpaired letters. Then when we try to when we copy the pairing from the definition, so if we do it by induction, so we show by induction that if we processed some prefix, then this prefix satisfies this this P1. So then if we have a factor here and it points to some very much earlier element, well, somewhere much to the left, then we just copy the elements. There were no two, those two first are paired, and we copy the pairing. Since this pairing satisfied P1, then this pairing here copied also satisfies this P1, and this is fine. There are some problematic cases if the factors, with the definition of the factor is very close. So if we are just, let's say it could be that the definition is just two elements to the left. Okay, it cannot be one to the left because we did the preprocessing. But if it's just two elements to the left, then what could happen is that we cannot use this argument that the pairing here is the same as in the definition, because this factor and its definition overlap. But if we make some case distinction, then it turns out that it is fine, meaning that, well, it could be that those two elements are paired already, and then it's fine. It could be that this is a free letter, then we move one to the left. No, it cannot be a free letter because then, and unpaired, because those two should be, sorry. So the thing is that in any case, if something goes bad, then we pop this element here from here. And then if those, since we popped, then this means that those two are not paired. So this one is unpaired. And then after popping, well, those two elements get paired. And then just by moving just one element to the left, it turns out that for this one, the pairing is proper, and we copy the whole pairing to the whole string. Okay, so there is some simple case distinction in here, but this is fine. And so the last one is for the paired, so that the first two and last two are paired. And this is true because we explicitly remove the letters which are paired incorrectly. Okay, so we ensure that the factor begins with two letters that are paired and that are unpaired. Okay, so now it remains to compute what's the size of the produced grammar and observe that, well, some observations. First of all, that we shorten the string, by a constant fraction. In each one of such rounds. Well, and this is because there are no two consecutive unpaired letters, which means that a constant fraction of, well, like at least 1/3 of the length is lost when we replace the letters in the pairing by new letters. Okay, so there are just, well, some O of log n rounds. And the second observation is that if we have a factor and it links somewhere to the left, then all the new letters. So if, say, we give a new letter C here, then the definition is the same. So if there is a pair of letters inside the factor, then those two letters are paired exactly the same outside of the factor. And again, if this is again inside the factor, we can go by the definition and so on. So in the end, we introduce as many new letters well, different as the number of removed free letters. Meaning that, well, here we have some two free letters, and after when we replace those two new letters by just by a single one, then we used to have two free letters. Now we have just one. So we lost one new letter, but we need to introduce one non-terminal for this production. Okay, so the number of new letters, so the rules of the grammar is the number of removed free letters. So we just need to estimate how many free letters are introduced during the algorithm. But this is easy because when we are given some factor fi, then it can lose one letter to the left because of this preprocessing. And then when we start to process this factor, then it, in the worst case, this letter to which it points initially is right in the pair, so it will lose one letter. Then it could be that there is a unpaired letter, so it will lose another letter. And then for the third letter, this will already point to a letter which is paired, the first letter in the pair, so it will lose no more letters. So in total, to the left, we introduce at most 3 new letters, and to the right, we introduce at most 2 free letters, because we just we can remove some because of the pairing. The pairing is like that this is the first element of the pair, this is unpaired, and then we cut off here, so we introduce at most 2 letters. So in total, we introduce at most 5 letters for this non-terminal, for this factor, and one factor will be turned into a free pair in O of log fi rounds, because its length decreases by a constant fraction of in each round. So in total, we will introduce sum from I equal 1 to L logarithm of length of fi. And the sum of those lengths is equal to n. And then some easy analysis tells us that if we have L factors, okay, and we the sum of some numbers is n, and we take the logarithm of them, then this is at most L times log n over L. Okay, I've lost this big O notation somewhere on the way, but this is, of course, everything is up to some constant fraction. Okay, and yeah, that's it for the algorithm. Any questions?
Well, do you have any example of that?
Example?
Yes.
Example of
Really
LZ7.
helps.
Example of LZ77, or example of how this works?
Well, LZ77 we all know, but how this works, how your algorithm works.
If I could make a 10 minutes break, I could bring some example, like on some very small, well, not the whole run, but on let's say at least a couple of letters.
But you don't have a prepared example, because I suppose that's what the audience would typically ask you to show.
No.
Yes, because, well, I just really cannot, well, cannot see how you can explain this without an example. Like, yes. All right, LZ77 you can, but it's simple enough. But your algorithm is, after all, much more complicated. But actually, if you implement LZ77 really with a sliding window and you remove suffixes from the suffix tree, it's also something, well, not so easy to explain. All right, but, well, maybe after the break, or you're now switching to something entirely different?
I'm switching to something different, but then I guess we can make the break earlier. It should be in 10 minutes. Okay, so we can make the break earlier and I will have some, I think I have some partially prepared examples, so I can make it in 10 minutes, or at least check if I have it.
Well, I think it would be very nice if you could. Then, well, at least for me, that would be essential in understanding. I remember I once understood this. Well, so this is compression to LZ77. Also, you had, but is this the original algorithm you have? But I think you had this originally slightly different compression algorithm, or it was this one.
I'm not sure I understand the question.
Well, I mean, what was the first result using your recompression technique?
No, that was not the first, but this is
This
simpler.
was not the first, right? Yes. Because the first one, it was without LZ77.
Yes, and
It
I
was
wanted to
just
talk
recompressing
explain
SLP
it.
to SLP, right?
Yes.
Yes.
And I wanted to explain it in the second part.
I see. Yes. Well, then at least I haven't seen this one before. Good. It would be a shame if I did and I couldn't understand anything this time, especially since, well, I'm quite familiar with LZ77.
So this is the word, and it has only two non-trivial factors. Okay, so most are letters, which is usually the case. Well, it has three, but that one is not important. So here the one factor is that there is a BC which is repeated, and then there is this A, B, C, D, E, F, A. Sorry, it should not be B, which is repeated again. Okay, and so when the algorithm starts to purr, then first it makes this Z, the first letter, a free one. Okay, then it looks at the second letter, it also makes it a free one, but since the previous one is also free, then we pair them. Okay, then it goes to B. This is again a free letter, so it will make it unpaired. Then this is again a free letter, but those two are next to each other, so they will become paired. Okay, the same here. Here, this one will be paired. With this one, this F is a free letter, so it's unpaired. And then we will move here, but this is a factor. It has a definition earlier, and so convenient that those two are paired, so it will just copy the pairing, and the last letter is also in the factor is the last letter in the pairing, so we will just copy the pairing here. Then this I becomes a free letter, because, well, it's a free letter, so it will be unpaired. Then this A is the first letter in the factor, okay, in not until this one, until here. Okay, and the first letter of this factor, okay, so its definition is here, and unfortunately this letter here is the second in the pair, and we want the first letter in the factor to be the first letter in the pair, so we shorten this factor. Okay, we make this a free letter, we shorten the factor here as well, and make this a free, and since it is a free letter, we also check whether the previous letter is paired. It is not paired, so we pair those two letters. Okay, then we look at B, and B has a definition here. It is the first letter in the factor. Okay, so we can pair, so we just copy the pairing for the whole factor. Okay, this is the E, and there is F, which is free, and there is B, which should be paired the right, but this would be, that's the last letter of the pair. So we wanted the pairing to actually have, well, the last two letters which are paired. So we remove this B from the factor because it's, well, it should be paired. So this definition is shortened here and here as well. And then we look at F, and again, its definition, it's not paired, so it's not the second, it's not the last in the factor. So we remove also this F from the definition, and we create whatever the pairing we gave. And then we are here. Those two letters are free. So we move to F, we make it an unpaired letter. B is also a free letter, we make it unpaired, but since the previous one is paired, then we pair it as well, which is actually, those are differently paired than the ones on the right, even though those are exactly the same. And here the I, well, it's actually a one letter factor because it has some early occurrence. So, but we just we just make it this single letter, well, this factor of length 1, we make it into a single letter, which becomes unpaired. Okay. And then we make a new string which just has well, one letter per every pair and per every unpaired element. And it can be observed that if something is inside the factor, so for instance this one or this one, then it has also the definition which are here. Sorry, BC, so which are here and here. So this one and this one. So those two which are inside the factor, they do not count towards the number of new letters which are introduced because they have similar occurrences earlier. The same here, this BC occurs earlier. So when we make some new letter, let's say X, then the same X is here, here, and here. So for the number of those new letters, we just need to count this first one, which consists of two unpaired letters. Okay, so just the unpaired letters produce new, well, are responsible for the new productions which are added to the grammar. Okay.
So, and what do you have at the moment? So you have created like a new level which is twice as short, almost twice as short. And
yes,
then
then we iterate exactly the same construction on this new level.
So then on this new level, you again run the LZ77.
No, not again the LZ77. We use the factorization that we had. So since this was well paired and the definition was also well paired, then we just preserve the definition that we had.
I see, yes. So then it's just, so then the time, it's deterministic time n log n, something like that?
It's actually O of n, because in one, well, assuming that LZ77 is done in O of n, because in one round you shorten by roughly 1/3.
Right, you shorten, yes,
so it's
yes, of
n
course.
plus
So it sums up to n, of course.
And so on. So
yes,
it sums
yes.
into something linear.
Yeah, so it would be n log n if you had to rerun LZ77 again, but since
no, it wouldn't be n log n then, because you would still need to rerun it on the shorter instance.
Right, the problem yes, it would still be n.
But
yes.
the problem with rerunning is that here we introduce some, the number of non-terminals depends on the number of those free letters. And here we can bound the number, because we can say that we have at most, well, every free letter comes from a non-trivial factor. And for a single factor, we can bound how many times it's used. So how many times it produces new letters. If we were to rerun this LZ77, then it could be that we get a factorization which has a different number of factors. And then we cannot really say how many letters are, well, those free letters are created.
Yes, now I see, yes. Well, thank you, now it's clear.
Okay, and actually the bound could be, well, the constants which are there are quite small, so you can actually compute well, maybe not exactly, but you can give a roughly good estimation on what's the constant in front of the logarithm, and it's relatively small. Okay, but the problematic part with this algorithm, well, the good thing of the algorithm is there is one, I think it's simpler, because all the different other constructions that produce more or less the same result, meaning the approximation algorithm for the problem, they usually, what they do is that they try to balance make the SLP that's producing the string balanced, which means that they need to perform some operation to get a balanced tree, which is doable, although usually quite technically involved, like that you need to merge some balanced AVL trees in a balanced way, and it can be done, but it's quite well technically involved. Well, doable but involved. Okay, but the problem with this LZ77 factorization is that while it is well defined for strings, LZ77 it's well defined for strings, but for instance, if we try to do something similar like a tree tree grammars, so for compression for trees, then those SLPs can be generalized to SLTs, which are a tree variant of the SLPs, but then we have no reasonable candidate for LZ77, or at least not well established candidate of this LZ77. Do not have all those properties of the that one is smaller than the other, and there's simply no point to start with, to begin with. So here for the approximation algorithm, the idea was that we begin with this LZ77 and then it can be done. But if there is no LZ77 for trees, then we essentially do not know where to begin with. Okay, so the idea is that we will use some generalization of this recompression approach also to generation to the approximation of the smallest SLP, and then since we can generalize from the recompression to trees, which was done for context unification, then we can also generalize this algorithm to approximation algorithm for tree grammars, which is true. Okay, so the starting point is that if we have an SLP, then it has the rules of the form that x1 is equal to some x2, x3, x2 goes to x3, x5, and so on, that we have rules of this form. But one can also, and at the end it's something like x17 goes to a. But all of those can be seen as word equations. Okay, so we can say that x1 is equal to x2, x3, and that x2 is equal to x3, x5. And assuming that there are no useless productions and so on, then this has a unique solution. Unique solution, which is simply built bottom up. So we start with those ending productions which have letters, and then we can calculate exactly what each production produces. So we know what's the unique solution of this word equation. Okay, so if we have an algorithm which works for word equations, then it also works for SLPs. But the problematic thing is that this recompression based is highly non-deterministic. We used all those non-deterministic choices about whether something is empty or not, and what's the first letter, last letter, what's the length of the prefix. And all of those were done non-deterministically, which is, well, we just cannot do it if we make it for SLPs, because we want to have a polynomial time algorithm. Okay, but this non-determinism is used in exactly those three places. So firstly, we want to check if something defines an epsilon, so whether we should remove this variable. What's the first and last letter of this word produced, well, of the word produced by the non-terminal of the SLP, or what's the first and last letter in the solution for the variable in the word equation? And what's the length of the a suffix and a prefix, well, of some non-terminal in the SLP. And all of those questions, if we are given an SLP, then all of those questions can be answered naturally. Okay, so if so first of all, this is actually not true. So the substitution for the non-terminal is empty if this is actually not true. So if all substitutions for all non-terminals on the right-hand side are empty and there are no explicit letters, if we want to compute the first letter of what's being produced by some xi, then either it begins with letter, let's say b, and we know it, or it begins with some different non-terminal xj, and then this is the first letter which is produced by xj. We try to purge all the letters. Assume that in SLP we never use on the right-hand side non-terminals which produce an empty string. Okay, so then it simplifies then this makes this first statement true, so that non-terminal produces epsilon if it has an empty production. And if we want to look for the first letter, then we just either it's explicitly given there or it's the first letter of some other non-terminal. Okay, and if we want to compute the length of the a prefix of the word defined in the non-terminal by the non-terminal, then we need to essentially look how many letters are there. So if the rule is AA x5, then we need to look at those AAs and the length of the prefix of x5, of the a prefix of x5. If it spans the whole x5, then we should look at consecutive letters and so on. But what's important is that if we know what are the length of the a prefixes of all previous x's in the derivation that are used in the derivation, then we can compute this length of the a prefix just by from this information. Okay, so we do not need any non-determinism. We can compute all of that in a bottom-up fashion. Okay, so we can make the recompression also for SLPs. But if we want to make it efficient, and we want to make it efficient if we have a approximation algorithm, then several things can and should be done in parallel. So for instance, if we had the operation of block compression. So for instance, if we had something on the form AAA BBB, then in one block compression we would replace it by A3, and then in some separate operation we would replace this by B3. But there is no reason to do those separately. Okay, let's say there's also AA here. Because those maximal blocks of letters, they do not overlap each other, so we can compress all of them in parallel. Okay, and this is done for the word equation exactly in the same way as it was done before. So we just we do not compress. We do not think that we compress just blocks of A. We in parallel compress all blocks of all letters in parallel, and this works exactly the same as before. In particular, this is equivalent of doing it well, just letter by letter. Okay, so this is sound. If all of the blocks are non-crossing, then this is also complete. And to uncross them, so what we previously did is that if you wanted to uncross just the blocks of A, then we popped a prefix and a suffix. And now if we want to uncross all letters in parallel, then what we do is that when we look at X, it has some prefix A to L, W, B to R, and this is the first letter, well, L, R, R greater than 0. Then what we do is that we pop A to L to the left and B to R to the right. So we just look what's the first and last letter and pop the appropriate A prefix and B suffix. And then it's still easy to see that, of course, there are some special cases. It's easy to see that this makes all letters uncrossing because this W here just begins with a different letter than A and ends with a different letter than B, which means that there are no crossing. After popping, there are no crossing occurrences of blocks of neither A and B. Okay, and this can be shown by some simple induction as previously. So blocks can be compressed in parallel, which is great. And we would also like to compress pairs in parallel because, again, this is much more efficient. But the problem is that we cannot do it we cannot just do it for arbitrary pairs. So if we want to compress BA and AB and BA in parallel, and we have something of the form AB, 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 then this is a problem because those occurrences overlap. Okay, so actually each occurrence overlaps with something else. So we need to make some sort of a decision what to compress, and this is a problem because then this decision would have to be the same at different places, and there are different non-terminals and different variables. So this is in principle a problem. So we cannot compress all of those an arbitrary set of pairs in parallel, but we can do it if we and the problem here is that here A is the left letter and R is the right letter, and here that's the other way around. So B is the left and A is the right letter. And there wouldn't be any problem if we knew that A is left, B is right, or the other way around. Okay, so if we always could say whether this letter should be left or right. And this is supplied by saying that we partition the alphabet. So if we want to compress pairs of letters from some alphabet, then we divide this alphabet into into two subparts, well, separate. This is a partition, so they sum up to sigma and they are disjoint. So, and one of them should represent the letters that are left and the other the letters that are right. And we compress letters. We can in parallel compress letters such that one of them is in this left, well, the left letter is in the left subalphabet and the right letter is in the right subalphabet, because such occurrences do not overlap. And for the uncrossing, again, this can be done in parallel, but now we do not, we pop the letter to the left if it's from the second subalphabet. So if it's one of those, okay, this, if this A, if X defines some B, has a B as the first letter, then we pop it if it has this potential of causing a crossing pair. So if this B is from the second subalphabet, and the last letter we pop if it has a potential of making a crossing pair. So if it's from this second or left subalphabet. But again, this is more or less the same as previously. So we pop those letters, and again, it can be shown that afterwards, even for word equations, but also for SLPs, we have exactly the same. There is a corresponding solution, and moreover, no pair AB in such AB such that A is in sigma 1 and B is sigma 2 is crossing afterwards. Okay, so each such pair is non-crossing. So after this one popping, we can make in parallel all compression for each AB in this sigma 1, sigma 2. Okay, and this is, all of those proofs are just variations of those previous ones, so I will not spell them explicitly. Oh, something here got, sorry, this should be somewhere else. Something got wrong with the slides. No, that's okay. Okay, so we can make the pair compression just that. First we pop from sigma 1, sigma 2, and then we compress all those pairs in parallel. Okay, so if we want to make it on strings, so we can build SLP by just iteratively compressing blocks and compressing pairs from some partition. Okay, so here we need to explain how to choose a partition, but I will explain it in a moment. Partition. But this will be explained in a moment. But what we will do for a string is that firstly we will compress all blocks of letters which are inside this string, and secondly we will list letters which are again in W. So we will recompute the letters and then choose some partition and compress in parallel all letters which are in this partition. And of course, this creates an SLP. Okay, so first this part makes some new rules, those parts also make some new rules, and assuming we choose this partition at least reasonably well, not in a very stupid way, then we will compress something in the first step, compress something in the second step. So after some steps, we will eventually end in a single letter, which means that we will create an SLP. Okay, so the first problematic part is how to make this choice of the partition. So the first answer is that if we make it randomly, so if we make a random partition of this L, so every letter goes to the left subalphabet with a probability 1/2 and to the right subalphabet with probability also 1/2, then the expected length of the word after such a random partition is, well, a constant fraction smaller than the original one. Okay, so we can iterate this process, and in each step we will shorten by a constant fraction, so we will end after a logarithmic number of steps. And this is random, which is not such great because for the, well, randomized approximation algorithms are still fine. But nevertheless, this can be deamortized in the sense that we can make this random choice. We can compute a random choice which satisfies this property. And well, assuming that we have access to some counting sort or things like that, then one round of this algorithm can be done in linear time. Okay, so we can list the letters, compress blocks, and compress all those pairs in parallel in linear time. And in every step, we shorten by a constant fraction. So in total, we will again end up with linear time. Okay, but let's say that in most cases, we do not really care whether this is linear time or not. Okay, so how to show this crucial part so that the random partition gives you a constant fraction smaller word. So we begin with some word, and in first step we just shorten, we compute the maximal blocks and we shorten them, and just ignore whatever happens here. So what's important is that after this first step we get something which is shorter, or at least not longer than originally, and every two consecutive letters are different. So two consecutive letters are different. Well, because we made this block compression, and well, if two consecutive letters were the same, then they would constitute a longer maximal block before, so they should have been compressed. Okay, so if we look at two consecutive letters, they are different. Those are, let's say, A and B. Then the probability that AB is compressed, so is compressed, is equal to 1/4, because this is exactly the probability that this A goes to sigma 1, which has probability 1/2, and that B goes to sigma 2, which again has a probability 1/2. Okay, so those two are A and B are different, so those two are independent, so that the probability that they will go into sigma 1, sigma 2 is exactly 1/4. Okay, so if we look at the expected value of compressed number of compressed pairs, so this is the length of W minus 1 divided by 4. Okay, because for each one of the W minus 1 pairs, we have a probability of 1/4 that it will be compressed. So the expected number of compressed pairs is 1/4. Well, minus this one, because the length is, number of those pairs is length of W minus 1 and not length of W. Okay, and this is for the expected value, but we can also randomize it in the way that we can just consider, this is a standard randomization, so we can consider those letters, well, list them in some arbitrary order, and then just consider the letters one by one, and for each one of them, well, compute what's the expected value, assuming that C goes to sigma 1 and that C goes into sigma 2, and all the previous choices are already done, so we know to which pair goes A, to where A goes, where B goes, and so on. And well, and just choose the larger one. Okay, so those are some values. We can choose the larger one and choose the C1, whether it goes to sigma 1 or sigma 2 appropriately, and then we just continue, and in each step we raise this expected, we do not lower the expected value, we can even raise the expected value. So in the end we can probably deterministically compute something which compress at least this number of pairs. Okay, this is fine. So this is somehow a very well-known algorithm in disguise. So there is this well-known problem of max cut in the graph, in which there is a randomized algorithm which just puts the vertices into one part of the graph and the other part of the graph randomly, and then it has expected value of 1/4, and it can be derandomized. And if you think about it for a moment, then this problem can be reduced to a max cut, because the weight of the edges should be just the number of occurrences of different pairs AB. So this is just the same randomization of this standard textbook algorithm. Okay, but what about the analysis? Because there is the algorithm, and we have so far no idea what should be the well, how to bound its approximation ratio. And the idea is that on one hand we have this W on which we run the algorithm, and on the other hand we take G, which is initially the smallest SLP. Let's say in Chomsky normal form. Okay, so the thing is that it should be binary, that every rule is binary. And we perform the algorithm here. That's something with the string. And we do exactly the same on the grammar G. Okay, so we can perform those compression compressions, assuming that we also do the uncrossing, so that we make uncrossing so that those compressions are doable. So if we want to make block compression, then we first pop the maximal blocks and, well, the A prefixes and B suffixes. And if we want to make the compression for sigma 1, sigma 2, then first we make the as a mental experiment. Again, we do not know this grammar, so this is just as a mental experiment. We make the uncrossing for the sigma 1 and sigma 2 on G. Okay, so in parallel, we make the same algorithm on the string and on the grammar, so that all the time this grammar generates this string that we consider. Okay, and what are the costs? So since we have already a grammar and I will be talking about its rules, and I will say that a letter has some cost of representing it. Okay, so if we compress AB into C, then I will say that the cost of representing this C is 2 because it has a rule of size 2, and if we compress A into A3, then the representation cost of this A3 is 3, assuming we have this sort of production. Okay, and the main step, well, the main idea of the algorithm is that we assign credit to letters in G. Okay, so that if we have G, then every explicit letter in G, has 2 units of credit. Okay, and then if we replace some AB by C, and this AB has an explicit occurrence somewhere in the grammar, then this one used to have 2 credit, this has 2 credit, we need just 2 credit for this new C, and the 2 units of credit that is freed can be used to pay for the representation cost of this rule C goes to AB. Okay, so this credit is enough to pay for those simple rules which do not use the well, not for the ones that for maximal blocks, because those are somehow more problematic. And in order for the letters to have the credit, we need to also assign the credit. So when we make this pop of L1, L2, then from every non-terminal, we introduce at most 1 letter to the left and 1 letter to the right. And those letters we need to assign some credit to them. And in this way, we only issue O of G credit, well, because the number of non-terminals does not increase. Okay, so we issue 2 units of credit, well, to the left and to the right of each occurrence of the variable. Okay, and for the pairs, this is enough. So the letters, well, the compression of pairs uses the credit. We know how much credit is issued, and that's fine. The problematic parts are the blocks, because it could be that well, due to how the grammar looks like, we could introduce something like A to 100 and B to 2000 to the left and to the right, and we should assign some credit. And if we were to assign just 100 credit to the left, 2000 credit to the right, then this is not going to work. We need some constant bound. Okay, but this also doesn't take into the account how do we actually represent the blocks, because in principle we can construct very long blocks of B's, and it would be stupid to have this B just represented that B2000 is represented as B, 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 and so on. Okay, this is not a good idea. And we will use them more smartly. So when we have some sequence of A's that we want to represent, so we have some blocks that we want to replace by new letters, and we should also represent those blocks in some way. The idea is that if those blocks are A to L1, A to L2, up to A to LK, well, where L1 is smaller than L2, smaller than L3, smaller than LK, we add L0 equals 0, just to make the description more streamlined. And then, so the idea why we should represent it like that, how we should represent is that on one hand, it's easy to just have some non-terminals on the right, which will generate A to 1, A to 2, A to 4, A to 8, and so on. So just the powers. But it would not be so smart to use only those powers and just use the binary expansion and collect those powers, because it could be that somewhere in the grammar there's some very large power A to 1000, and then there is A to 1001, A to 1002, and those can be very easily produced by just adding some single letters to already produced strings. Okay, and there is no reason to use some very large, some large number of non-terminals just to express them in binary. Okay, so instead of expressing everything in binary, what we do is that we will be expressing the differences. So if we have those blocks of A's which are ordered by the length of the blocks, what we will do is that L to I, it will refer to the previous one, so L to I minus 1, and there will be an explicit block of there will be block of A's here of length Li minus Li minus 1. So we have the difference, but this is represented in binary. Meaning that we will concatenate those non-terminals for powers of A in order to get this A to, well, appropriate power. Okay, and up to a constant fraction, the length of this will be, well, 1 for, well, the cost of representing will be, so here it is a production, actually, not an equality. The production will be 1 for this non-terminal, and some, well, roughly logarithm of this difference for this other non-terminal to represent those in binary. Okay, there are some constant fractions because we actually there is some rounding up and so on, but up to some small constant fraction, this is the cost of how we would like to represent the blocks. Okay, and the problematic part of this representation is that it's difficult to bound its size. Okay, so although it's actually a natural way to do how to represent the blocks, maybe there are also some natural ones, but this is a not so bad one. But the problem is that it has nothing to do with the grammar. So we have some grammar in our algorithm which is used for we have some algorithm which is used for the analysis, but it has nothing to, however it expresses those blocks, it has nothing to do with how we are actually doing that. So we will define some different representation which actually uses the way how our mental experiment algorithm treats the grammar, and then we will compare those two representations and actually show that the one which is used by our algorithm is smarter than the one which is based on this abstract on this SLP which we keep as a mental experiment. Okay, so this representation will be based on this. So the way we will represent those powers of A's will be based on the grammar G. So we have some grammar G which defines the appropriate word, and we will define one non-terminal for every maximal block which will be okay, this G is turned into G prime due to popping, and then is turned into G prime due to popping of A prefixes, well, of prefixes and suffixes. And we will introduce a new non-terminal for every popped prefix and suffix. Okay, so if there is some X which defines a word A to 3, some word A to 7, then we will have a non-terminal for A to 3 and A to 7. So A3, A7 will be there because we will pop them from the non-terminal. And additionally, we will have a non-terminal for every maximal block of A's, which is in the grammar after the popping of everything, so just before the compression. So if we had this X, there is another X, and we pop, well, there's A in between, there's A here and some A here. We will replace this X by X, A to 3, A to 7, A to 3, X, A to 7, A, and there's one A here. And we will introduce a non-terminal for every length which occurs somewhere here. So we will have A4, here it is 8, 11, and hey, here it is A9. Okay, so we introduce, and again, this A to 3 will also have its non-terminal, and this A to 7 will also have it non-terminal. Okay, and this also shows more or less how we will define the rules. So here we have A to 4, and this A to 4 will have a rule of the form A3. And this is reasonable because this is exactly the way how we get this A4, right? And here this A9, it will have a rule A7. But the problematic part is here. So in between two non-terminals, it could happen that we have a very long block of A's, which is created because we matched some popped prefix and some popped suffix. Perhaps there were some A's in between, and we get a much longer block of A's. And here, this one is just expressed in binary. Okay, for this one, we use just binary representation. Okay, so without this A3 and 7, well, just because. Okay, so once again, we will express those letters either by referring to some other non-terminal and adding letters which correspond to letters which were there in the, well, to explicit letters in the non-terminal, in the SLP, like here and here, or we'll just use the binary expansion if they included these two such popped prefixes, well, a popped prefix and a popped suffix. Okay, so and the note here is that what's the cost here? So when there are two blocks, when there are two blocks, so in the second case, when we have this binary representation, then this requires some extra cost, some extra credit. We will estimate it separately. And for the first one, it's enough just to use the credit which is already on the letters, because, well, this letter has a credit, this letter has a credit, this letter has a credit. We can assign one credit to the whole block. We cannot assign 3 units, well, 6 units of, we cannot assign units of credit to every letter in the popped A prefix and suffix, but we can assign just 2 units of credit to the whole block. And then this also has a credit, this has a credit, and this credit can be used to pay for the whole rule, because this one is 2, this one is 2, and we need 2 for the A4, and the remaining 2 can be just used to pay for how this rule looks like. Okay, and now those 2 representations can be compared in the sense that the one that we are using is actually smaller than this G-based one. And those are just simple calculations. So for the G-based one, what we can do is that we can imagine that we represent some lengths, and the cost, we can order those points as natural numbers. And the cost here is that if we have a length, some L1, L2, L3, there's also L0, which is equal to 0, just for the sake of consistency, L4, L5. And then the cost here is just the, well, 1 plus the logarithm between those 2, logarithm of the difference. Okay, and how much the representation, this G-based representation, uses. So first of all, each of those numbers is still there, because since it represents every popped prefix and suffix, but it also represents every maximal length, well, every maximal block which is in the grammar. This maximal block is non-crossing, so if it's in the word, then it also appears somewhere in a non-crossing way, which means that in the SLP in the non-crossing way, which means that all of those lengths are also expressed using this G-based, are also represented using this G-based representation. And here the cost could be, but it also could have some some different nodes. Okay, so we are using those that previously, but also perhaps some other lengths. And the cost here is charged not necessarily towards the nearest neighbor, but to some neighbor. Some goes to here, this one could go here, this one could go here, and so on. But in general, they are assigned somehow. This one could also have a edge, let's say here. And the first observation is that it's something is between those 2 nodes that we want to represent. Then we can shorten this rule. Okay, and those rules, and there are 2 ways how they can be represented. One is that this is this well, global rule that is expressed in binary, and it has just the edge to 0, and then it has the cost of 1 plus logarithm of L. And otherwise, if they are the edge is towards something different, some different node than just the 0, then the cost is just the difference between those 2 nodes. So if this is L, this is L prime, then here the cost on this edge is L minus L prime, because this is due to those attachments of the explicit nodes. Okay, and then we just change this G-based representation into the our representation, and we lower the cost, we lower the used cost all the time. So firstly, we can observe that we can shorten all those edges, and instead of representing through this, we can represent through the closest one that we also want to represent. Okay, so this one is then reduced to this one, and the cost is then still L minus L prime when those, this is the definition, well, the source and the target. Okay, and this of course only decreases the cost because we shorten those edges. And here also, if it goes to the first rule, then we can switch it to the previous that we all, well, to L0, then we can switch it to the previous that's also represented, and then the cost is 1 plus logarithm of the difference. Okay, so 1 plus logarithm of L minus some L prime. The second observation is that if we have L minus L prime, wait, maybe 2L minus L prime. Let's say it's always 2L minus L prime just for the sake of calculations, then this is smaller than, sorry, that this is larger than 1 plus logarithm of L minus L prime. So we can replace every cost which uses this difference by the 1 plus logarithm of the difference. There might be some constant overhead, but constant multiplier overhead, but this is not important. So we can replace every such additive term, well, just difference by 1 plus logarithm of the difference. So this would be 1 plus logarithm of the difference. And then what we should see is that if we have several such edges, then the cost of, if we have 1 plus logarithm of this difference and there are several such steps in, below, then the cost above is smaller than some of those costs below. Okay, and this is because of logarithm is convex. So what we want is just, we want those edges, so between those designated vertices, and there could be some edges somewhere here as well. Okay, then they go using several steps, but then this is 1 plus logarithm of the difference of the whole, and in each of those smaller steps we have 1 plus logarithm of this smaller difference. And then if we calculate it, then well, we can just shorten two such consecutive edges into one. This decreases the cost. We can make it well as many times as we can, and then we, in the end, we will end up with just one edge, and all the time we just decrease the cost. Okay, so after some number of steps, we will, all the time we just decrease the cost, and in the end we will end up with the grammar which represents everything in exactly the same way. Okay, so the cost of this G-based representation is smaller than the cost of the original representation. On G-based, sorry, what we are using is smaller than the cost that's based on the algorithm. So the only thing that remains to be estimated here is what's the size of this extra credit. So I'm claiming that this size is the number of rules of the grammar times the logarithm. And why it is so? So if we look at some fixed rule, so there is a fixed rule, and this extra cost can be imposed only when there is some there are two non-terminals in the rule, and there is some x generates some suffix of a's, and y generates some prefix of a's. If there is any letter in between, then it again should be a, and then this becomes this block then we need to represent separately. And and this, of course, can happen several times during the algorithm, once for the second time, and so on. And if those blocks have lengths, and the cost of such representation is 1 plus logarithm of, well, r plus 1 plus l, we can forget about this one, because first of all, it's, well, comparable with the size that, well, comparable with this logarithm. And secondly, we are using only, in total, we will be using only logarithmic number of compression steps. So all those ones, when we sum them up, they will end up into something which is logarithmic. And then when we sum by the number of rules, then we'll get something of the form g log n. So all those one add up into something small. Okay, if this is just one per phase, then that's fine. So what we need to deal is those logarithms that potentially they could lead to something like log square of n. So imagine that in total we have that those lengths are L1, L2, L3, and so on up to Lk. And the thing is that if we okay, and then the sum of those logarithms of Li's, then this is the same as logarithm of the product of those Li's. But the thing is that when we replace those those letters with a new symbol B, and then something happens, and then we have a lot of new letters. So CR, CL, some primes, and C in between, and then we again replace them. Then the thing is that we look at all those letters. They represent something in the original string. So if we say that this A represents something in the original string, then the length of this representation is at least 1. So this A represents a substring of length at least 1 in the original string. So whatever we compressed here, so those L1s that we compressed, then they represent at least L1 letters in the original string. But when we compress those L2 letters, then we have some B to L2, but one B generates something which has at least A to power L1 inside. So this B to L2 represents at least L1 times L2 letters in the original string. The original string. Okay, because one B represents at least one A to power L1. So if you have L2 copies, then we have at least L1 times L2 letters A somewhere inside the original string, and so on. If we have if then we make compression of L3 letters, then we will get at least L1 times L2 times L3, and so on. Which means that in the end, the product of all those Li's from I equal 1 to k, this is smaller than n, where n is the length of the whole string. So if we take the logarithm, this means that the sum of logarithms of all those i's is at most logarithm of n, which is fine, because this means that for one rule, there is at most logarithm assigned in this way. So when we sum up over all rules, then we will get g times log n with some constant overhead, which is what was to be shown. And in the end, this means that our algorithm in linear time produces a grammar of size g log n. If we make this analysis slightly more precise, then this could be done to n over n divided by g. Some things are separate, and when estimated more precisely, then this will lead to n divided by g. Okay, which is again the same approximation ratio as before. Questions, comments? I have a small comment, but this in a moment.
Well, so, well, of course, you know, I would want to see an example, but maybe let me even make it a little bit more concrete. So it would be nice to have an example where this procedure, provided that the non-deterministic guesses are correct, well, I mean, are successful, that this procedure produces something significantly smaller than if you convert an LZ77.
So actually, I had a student implemented all of that, and it turns out that this is usually much better.
Well, that's of course something, well, no doubts. I just want to see an example, not because I doubt, but because I want to understand how this works.
There's the problem, but what would it mean that it's smaller than that the grammar is better than the one which is based on LZ77?
Well, because you have an algorithm which converts LZ77 deterministically into a grammar. And so I would like to, yes, LZ77 is unique. So it's enough to present one single string. Yes. And yes.
So I'm afraid that nothing, I do not have any example in which it's meaningful. I mean, I can digest back an example, recreate an example, but I don't think there is any idea in this example. So I don't believe in examples as much as you do, at least in some cases.
Well, but well, I just had this general question to you. How do you teach suffix trees? Can you teach a suffix tree without an example? I think your algorithm, it's like the suffix tree construction. It's something sophisticated, and you need an example to, well, to teach it to anyone.
But I wouldn't teach about suffix trees on an example. I mean, you add a letter and then you make some computations. I don't think that having an exact example actually gives you any more understanding. In some, if the algorithm is much involved, then an example doesn't actually tell you anything because it's almost random inside.
Well, the thing is, of course, to create an optimal example so that every feature of your algorithm would be used exactly once, and so you can illustrate it on a single run. That's something, because, well, I suppose eventually you should write a monograph on this, shouldn't you?
I wanted to, but I probably will not.
Yes, well, maybe you should mobilize your students to create these examples. If your students manage to understand this, maybe they can somehow, well, digest it out of their understanding.
I will try.
Yes, that would be really very nice.
So since there is 5 minutes, so maybe I will not give the algorithm, but at least how it can be done. How the tree grammars are defined. So for the idea of the context-free grammar, maybe I will give an example first, is that when you have some tree, which already has some nodes defined, but it also has non-terminals somewhere inside, then the non-terminals, they also have some sort of arity, and they have as many children as they have the arity. And when we apply the rule to this node, then it uses parameters exactly as many times as, well, it has as many parameters as it has the arity, and it uses each parameter only once. Okay, so in a sense, what we are doing is that we are crossing out this single node and we are replacing it with this subtree, which it has in its definition, and then we just reattach the subtrees of this node A at appropriate places. In principle, we could switch the order, like it could be y2, y1, but why should we do it? So we just, okay, so this is the rewriting that we have for context-free tree grammars. That we take the children, we replace the non-terminal by some subtree, and the subtree is missing some arguments. This is exactly the same number as the number of arguments of this original non-terminal, and we just reattach the subtrees appropriately. So usually in the same order, but in principle we could also permute them if the rule says so. Okay, which means that we have some ranked alphabet. So every node has a fixed arity. Non-terminals also have the arity. And if we have a rule, then this tree for the non-terminal of some arity k is also a linear pattern in the previous meaning, means that it's a tree with k missing arguments. And this rule also can use non-terminals, so some other non-terminals from the grammar, and of course it needs to preserve the arity. So if we have it here, we could also use some node C here, which is a non-terminal, assuming that the arity of this C is also 2. And then this would mean that we would have non-terminal C here as well. Okay, and such trees could be also, we could use this notion of tree grammar also to define as a way of compression, assuming that those straight line tree grammars that they define exactly the same string, which will be formalized in the same way as previously. So there is exactly one production, well-formed production, so the arity needs to be preserved. And also we have some order so that we do not cycle. Okay, this rule size is perhaps not that important. And there is a natural problem is that we are giving a tree T and we want to produce, again, generate an SLT capital T, well, such that this capital T produces the given tree. And this, well, LZ77 based algorithm doesn't generalize to this case, mostly because there is no LZ77 for trees, at least not a standard one. And this recompression based algorithm, it actually does generalize to this setting. We just need appropriate compressions, and in the end the approximation ratio is more or less the same, so it's L RG R times logarithm size of the tree divided by RG, but this R is the arity, is the maximal arity of letters in sigma, or of letters in the tree T. That's the same. The reason why there is this RETR is because things get more complex when there are non-terminals which have many arguments, and then we need to somehow change them. Well, in the analysis, this arity matters. It can be reduced to the case when this arity is at most R, and this comes out as a constant. And those compression operations are exactly the same as we used for context unification. So there are the two that we already used, so the spec compression and block compression. And this leaf compression is also utilized, but in a more efficient variant. So we compress as many children. Well, first of all, we compress in parallel, and we do not compress just a single child, but all the children which are leaves at the same time. And otherwise, the analysis of the algorithm is exactly the same as before. So we, on one hand, we just run the algorithm on the string, on the term, and on the other hand, we start with the smallest grammar that generalizes it, which generates it, and then we apply the rules on the grammar as well, so that in order to compute how many rules we actually produce. And this was the first algorithm for this problem. So without this approach, it seems difficult to make some approximation algorithm. Okay, and that's what I wanted to say today, I think. So are there any questions?
So we have two algorithms that construct a small
approximation of the smallest.
Yes, and like the second works fast, we produce small approximations in most cases, not asymptotically, you mean. But other cases when it produces a better approximation, like it's like, is it true that there are some restricted set of cases where it produces a better and a very good approximation, even better than just log and divide by G?
I cannot give any good family. So probably if you try, then probably you will find some cases in which one is better than the other. Especially that this LZ77 based, it has a really very small constant. So the constant that come out from this approximation of this recompression base are much larger. So if the approximation ratio is bad, then most likely this LZ77 will turn out better. But anyway, if you make it on any set of real life data, whatever it is, then there are several heuristics and all of them work much better on all of those data.
Okay.
So there is some reason why in practice it's usually smaller, because I presented the analysis which focuses on the grammar, but you could also do this analysis in terms of LZ77 and it should also work. But there are also some generalizations of LZ77, like two-directional LZ77. And then it could also be shown that this grammar has the same approximation ratio, well, with respect to that, well, bidirectional LZ77. So in fact, it has a slightly better approximation ratio, but it's more difficult to show.
Mm-hmm.
Well, thank you very much for the lecture. So, well, I remember once I was able to understand it partially, but this was not really well. The knowledge didn't survive the time, unfortunately. Well, but I suppose that's really the example. That's what is needed, because, well, actually, I can only admire you so that you can create such an algorithm on such a level of abstract thinking that you can fit it into your head without having an example. I wouldn't be able to. Yes, but I think, well, just to enlarge the audience, a good example is needed. Because, well, like for suffix trees, really the examples, well, since this is a standard subjects, the examples have been so much perfected that it becomes easy to understand it. Although, well, it's probably as difficult as your algorithm.